Hello everyone. So welcome to the fourth live interactive session for the course Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So I'm hosting these live sessions, and today is the fourth week, and so this is the course outline for the course of structural geology. As you can already see that we have already covered the first 3 weeks, which was actually the basic concepts of structural geology, measurement of structural attributes, and then concept of strain. So today's week is primarily focused on the concept of stress and its relation with deformation, and whatever we will be discussing today or whatever you have already learned in this week uh, from the course material regarding stress and its relation to strain, that is the crucial knowledge that you will need to carry on the further discussions that is related to the rheology of materials and rocks, and what are the different types of deformation mechanisms that we generally see in minerals that are also similar to other kinds of materials like metals and alloys, and then how these deformation mechanisms are generated in response to the strain, and how the strain and the generated how the stress and the consequence of stress, that is the strain, together helps in development of the foliations and lineations, and how ductile deformation occurs, especially folding, boudinage, and shear zones. And then also, at what point do the ductile deformations set in and how they are being different from brittle deformations such as fractures and joints or faults. And then we will also know something about a phenomena called brittle ductile transition in crustal or mantle rocks that helps in localization of strain, and through the process of localization we get to see ductile shear zones. And ductile shear zones are something which is very much important for understanding ore genesis and ore mineral concentration in host rocks, right? And after that we will also learn about the lithostructural mapping, how mapping is being carried out in the field, and also from observing or compiling geological data in a large regional scale from remote sensing data to actually acquire a map on how the ore minerals are being distributed within host rocks that has experienced significant polyphase deformation, and also its relation with the shear zones. It may be outcrop scale shear zone, or it can also maybe a meter scale or even kilometer scale thick shear zones where these ore minerals are concentrated. So in a way, this fundamental knowledge is about the stress and strain and how materials behave under pressure and temperature would actually help us to understand how we can better acquire knowledge about ore mineral concentration within rocks, and how it helps us mining these resources, these energy resources that we commonly use from the nature. So, as we have already discussed, that these live interactive sessions are weekly sessions, and these sessions are to be held for 12 weeks straight, because parallel to the duration of the course itself, which is for 12 weeks. And this is the fourth live session. It's on 15th August 2026, and we will continue the live sessions on each Saturday at the same time. So talking about today's live session, so today's live session is mostly focused on the concept of stress. So in this week we have already learned about the concept of stress, surface forces and the body forces, the concept of traction, concept of shear, which also includes the concept of scalar, vector, tensors, stress on a surface and stress at a point, stress equilibrium conditions, principal axis of stresses, stress ellipse and stress ellipsoid, stress matrix, normal stress and shear stresses, stress invariants, and then very important concept regarding the eigenvectors and eigenvalues, and stress components on a plane, determining the principal stress components and its relation to the conjugate shear planes, and finally the establishing the relation between the active stress and the consequence of stress, as in the deformation or the strain. So based on these summary topic on these various topics that we have already covered in weeks 4 content for the course structural geology, I have designed several multiple choice questions. So we will go through these questions one by one, we will solve them, and as we have already been doing these things, like I will show or present a question, I will give some time for you to think what will be the correct answer, and then we will discuss what is the probable answer and why is it so. So let us begin with today's question answer session. So the first question is, traction acting on a plane within a stressed body is best described as a vector quantity that depends on the orientation of the plane, a scalar quantity independent of the plane's orientation, a body force acting per unit volume, or a tensor of rank 2 defining stress at a point. So this question comes from the point of view of traction. So you have to know that stress and traction, they are not the same expression of force per unit area, they are different. So keeping in the mind, if you have already gone through the lectures, you have already understood what is traction and what is stress. So if you know the difference between a stress and the traction, you can always we can go for the answer. So I will pause for a minute and I will let you think which will be the correct answer. Then I will also discuss which is a probable correct option to this question.
Option A.
Option D.
Option A.
Option A. Okay. Yeah. Option A is the correct answer. So a vector, so traction is essentially a vector quantity that depends on the orientation of the plane. Why so? Because traction is the force per unit area acting on a specific plane through a point, right? And unlike the stress tensor, which is a fixed property of the point, traction is a vector whose magnitude and direction change with the orientation of the plane considered. And the same stressed point can have very different traction vectors on differently oriented planes. So the thing is, when we consider a stress tensor, a tensor of rank 2 is actually a 3 by 3 matrix that has 9 components, and each of these components, based on the orientation of the planes that are being considered while making the 3 by 3 matrix, so each of these components is a different traction unit. So you combine all the tractions to get a stress tensor. So that is why traction is also a tensor but of rank 1, and any tensor that has rank 1 is known as a vector, and any tensor that has rank 0 is actually a scalar. So in terms of tensor, if you speak in terms of tensor, then tensor is a thing that describes three different things. One is the magnitude, the other is one direction, and the another is another direction. So a stress at a point has a magnitude but also has differently oriented directionality, based on which we calculate the resultant traction at each point. And by adding up all the components that we are considering for each and every plane that constitutes the three-dimensional uh, you know unit reference cube with respect to which we actually estimate the stress at a point, that is essentially a rank 2 tensor, because it contains information regarding the magnitude of each component and the direction of each component. So there are multiple components of direction, not only just a single component of direction, but for a rank 2 tensor, which is a stress tensor, it has a multiple component of directions. But traction only has one component of direction and one component of magnitude. So if I repeat again, scalar is only magnitude with zero components for direction. So that is why it is zero rank tensor. A vector has magnitude plus one component of one component of direction, and that is why it is a rank 1 tensor, also known as a vector. And a stress tensor has magnitude, right, and several components of direction, which is at least two components. Because for each of these traction components, if you see for a stress tensor, there are two perpendicular directions that can be specified when we are considering the stress tensor, right? Sigma xx, sigma xy. I mean, sigma xx is one stress, one traction component, but then there are other components, that is tau xx, tau xy, or tau xz and tau zx, these kind of components. So there are two perpendicular orientations based on which we can actually calculate the components of direction for that same magnitude of traction. Combine all these things and you will get a tensor. So stress tensor rank 2, traction only rank 1, because it has one component of direction, right? So that is the fundamental difference between a tensor and a vector. I mean, all vectors are tensors, but not all rank 2 tensors are vectors, right? Okay, so let us move on to the next question. So question number 2 says, which of the following is an example of a body force acting on a rock mass? Frictional traction resisting slip along a fault plane, fluid pressure acting normal to the bedding plane, gravitational force due to the mass of the overlying rock column, or push exerted by a moving glacier margin?
Option C.
Yes, option C is the correct answer. Gravitational force due to the mass of the overlying column. So this is a body force. This is not surface force, right? Body forces act throughout the volume or the mass of a body, just like gravity or inertial forces, right? And body forces are usually expressed per unit volume or mass. So if you consider gravity, so if you calculate what is the force of gravity, so the formula goes like force, gravitational force is equal to gravitational constant multiplied by the mass of one object by into the mass of the another object, and you divide the entire thing by the square of the distance. It's an inverse square law following force, and that's why force every body force that actually becomes a function of the mass of the object is can also be described as a central force which follows the inverse square law of central forces, right? So it has a potential, right? So the force creates a field, and the ability of that field to exert a force on a on a mass of an unit object is the potential, right? But on the other hand, surface forces like friction on a fault or fluid pressure on a bedding plane or push from a glacier, whatever these are, they act on only on the boundary or the contact surface of the body. So that is very different from, say, anything that is a body force. Surface forces are heavily dependent on the orientation orientation with respect to the plane of the force that is being applied, right? So you always consider the normal vector of the plane onto which the force is being applied, and based on the angle between the normal to the plane and the direction of the force, this will actually uh, it will control the entire mm, resultant force, or the entire, not the force may remain the same, but the stress will depend heavily on the orientation with respect to the normal to the plane. That's how we can resolve the shear and the normal stress components, and that is why anything that is involved via some push or some any force acting along an interface, that, that can be friction or localized fluid pressure on a certain plane. So wherever there is an interface involved, things generally go for the surface forces, whereas body forces are expressed homogeneously over the entire mass or the volume of the object. In similar way, hydrostatic stress is also a body force because it does not depend on the direction, right? So body force, like gravity of course exerts a direction to which it is attracting the mass, but then within the mass, that force has no control on the resolution of different stress components. So within the object, gravity or the hydrostatic stress or the mean stress, they will act homogeneously all the way to the entire volume, and it will not be dependent on the orientation with respect to the plane and how the forces are being applied. Okay, so the state of stress at a point within a deforming body is completely described by a tensor of order 0, 1, 2, or 3. And this is quite easy because we already discussed this.
Option C.
Yes, option C is correct. So it is essentially a rank 2 vector, right? So stress relates two vectors, the plane's normal and the traction on the plane. That was what I was talking about. Stress at a point, it has one magnitude and two components, one perpendicular to the plane and the other one is the parallel to the plane. So one is the normal component and the other one is the traction component, right? So there are two directional components, and that is why it is a rank 2 tensor, because it has two direction components other than the magnitude. But if I consider only the traction, it will have only one component because it is a linear thing, right? It involves only one direction. And if we just consider these two directions, so to relate these two vectors to the stress, I mean, if we just need to uh, need to add up the resultant stress, I mean the magnitude of the resultant stress with these two vectors, we generally do that via a linear transformation. That's how the 3 by 3 matrix comes into the picture. And this requires a second order tensor, rank 2 tensor. So we need to construct a matrix, and that is being done via linear transformation. And this is obviously is represented in a 3D as a 3 by 3 matrix of 9 components. But within that 9 components, 6 components remain independent and the other 3 components cancel out due to the symmetry of the tensor. So it's an orthogonal matrix and it's a symmetric matrix, and that is why there are only 6 independent components, because if we consider 6 planes, right, right, this side, up and bottom, left, top, this left and right, this kind of thing. So there are 6 planes. Each plane has its own, independent component. There will be 3 independent normal stress component and 3 independent traction component. That's how we get 6 independent components within a stress tensor. And the other 3 components are opposite to the previously mentioned traction components. And that is why they cancel out. Because in normal state, we consider that the stress at a point is maintaining an equilibrium. So if there wasn't any mechanical equilibrium, then the cancelled out components would not have been equal to the independent components, right? So that is why, due to maintaining, I mean, if you have to maintain the equilibrium, they must cancel out in terms of their direction and as well as their magnitude. And that's how we get, although we get a 3 by 3 matrix, but it generally has only 6 independent components. And since this matrix is symmetrical and it is orthogonal, and that is why we can derive a determinant from that matrix which gives us the magnitude of the entire stress tensor, stress at a point. If you calculate the determinant of that matrix, you will get the value. and from the matrix itself you get to calculate the since it is a three-dimensional matrix and it is an orthogonal matrix, you also get to calculate the eigenvectors. So by calculating the determinant, you get the magnitude, and since it is a symmetrical matrix, you can calculate the eigenvectors as well. And these eigenvectors will match the principal stress axis orientations. So from a stress matrix, if you calculate the magnitude, that will give you the resultant magnitude of the stress at a point. And the eigenvectors are actually useful to know the orientation of the perpendicular, the direction of the principal axis of stresses. That is sigma 1, sigma 2, and sigma 3. Right? Okay. So coming to the fourth question. A single vector is insufficient to describe the state of stress at a point because stress has no directional properties. The magnitude and sense of stress change with the orientation of the plane considered. Option C, stress is a scalar quantity. And D, stress does not vary with depth. So a single vector is insufficient to describe the state of stress at a point because the reasons are given.
Option B.
Exactly. Option B is the correct answer. The magnitude and sense of stress change with the orientation of the plane considered. A vector has one fixed magnitude and one fixed direction, right? But at a single point, the normal and shear stress values change continuously as the orientation of the reference plane changes. Only a tensor can generate the correct traction vector for every possible plane orientation through that point. Right? Now there is a catch, and the catch is this question is fundamentally flawed because we are not mentioning whether the stress at a point is in equilibrium or not. So if and only if the stress at a point is in an equilibrium, then we can describe the thing entirely with a symmetric tensor. But if that stress at a point is not in mechanical equilibrium, then we cannot use these symmetric tensor to describe the entire state of stress at a point. So all these assumptions, all these calculations, they emerge from the assumption is that the stress of the stress at a point generates an mechanical equilibrium condition around that point on an infinitesimally small cubic volume. Right? That's how the assumption is. But in reality, these assumptions may not hold for the fact that there might not be an equilibrium maintained. Now the thing is, why does these assumptions generate, and why in many cases it holds true? The answer is because we consider an infinitesimally small volume. That means we take we construct a cubic volume with respect to a Cartesian coordinate, and then we calculate all these traction components to design or derive the matrix. And after that, once we get these values, we use the directions as the variables, right? The xyz variables, and then we put a limit, as in the volume of this entire cube is tending to 0, and then we simply give the estimate of the rate of change of these traces, I mean rate of change of each of these traction components, describe the tensor. So that is why, since we are considering an infinitesimally small volume, it generally follows the equilibrium condition because it is very small. If the area expands large enough to cause any sort of distortion with respect in terms of the orientation of the plane or uneven geometry that cannot be um, properly mapped using the Euclidean geometric theories, then the condition for equilibrium may not hold, and that's why we always consider a tiny volume, or may I say as the infinitesimally small volume. And that at that case, or at that point, everything will generally tend to maintain an equilibrium condition. Okay, so moving on to the next question. Yep. So for a body in static equilibrium with no net moment acting on it, the stress tensor must be symmetric, which requires sigma xx is equal to sigma yy is equal to sigma zz. Option B, all shear stress components equal 0. Option C, sigma xy is equal to sigma yx, sigma yz is equal to sigma zy, and sigma zx is equal to sigma xz. And option D, sigma xy is equal to minus of sigma yz.
Option C.
Yes, option C is correct. Why not option D?
Because there is a negative sign.
Yeah, but if you think, a negative sign may in I mean negative sign would cancel each other, right? But even though there is a negative sign which actually says that mathematically they would cancel each other, that would reduce the net force to zero, then why the negative sign is being avoided? Because mathematically it is convenient, right? If you just cancel out these components, then you will only get the principal components.
Don't know, sir.
The thing is, if you put two different orientations, the thing will start to rotate, right? You're, I mean, physically, if you think about, mathematically it is okay, but if you just think about a cube and you are applying two shear stresses in the opposite direction in the same magnitude, what will happen? It will rotate, right? So it will simply represent a rigid body rotation, and that is not an equilibrium condition. So that's why we need equal magnitude and equal direction components, and that is why option B is correct, because these are mathematically equal. These maintain the symmetry, and also they balance the moment. So balancing the moments about each axis for an infinitesimal stressed element shows that the two shear stress components acting on mutually perpendicular planes pointing towards or away from their shared edges must be equal. It has to be equal. That's how the moment will be balanced. So the net moment acting on it has to be zero. And if we just simply put the negative sign, that means we just reverse the direction, the moment will not be zero. The position will be fixed, but the moment will not be zero and it will start rotating. And these pairwise equality, that means sigma ij is equal to sigma ji, is what makes the stress tensor symmetric. So if we add some component that has negative, I mean opposite directions, the stress tensor will not remain symmetric, and as a consequence to that asymmetry, it will start to rotate, right? And this symmetry, of course, reduces the stress tensor or the 3 by 3 matrix into 6 independent components that I already said in the last question as well. Okay, so moving on to the next question. Yeah. On any principal plane passing through a stressed point, the shear stress component is equal to the mean stress, maximum, equal to the normal stress, or zero.
Option D.
Yes, option D is correct. It has to be zero, right? Because principal planes are defined as the planes on which the traction vector is purely normal to the plane. That is the definition. Right? So there are no parallel to plane traction components, only normal traction, no shear traction. And by definition, the shear stress component on the principal plane is zero. And in that case, the normal stress on this plane is a principal stress. And the direction of that stress is the principal axis of stress. Right? Okay. So moving on to the next question. Question number 7. The three mutually perpendicular axes of the three-dimensional stress ellipsoid at a point correspond to the three principal stress directions, the planes of maximum shear stress, any three arbitrarily chosen orthogonal reference axes, and option D, the orientation of the conjugate shear fractures. So it is related to the last question as well. Okay, so of course the option A is the correct answer, because the three principal stress directions are the three-dimensional perpendicular three perpendicular axes of the stress ellipsoid. Right? So the stress ellipsoid is constructed by plotting the traction vectors for every possible orientation through a point, right? And it's three mutually perpendicular axes coincide with the three principal stress directions. Their lengths are proportional to the magnitude of these principal stresses. And that's how we get a stress ellipsoid. So the largest axis, we generally consider that as the sigma 1. The magnitude of the length of these largest axis of the stress ellipsoid will be the sigma 1. The intermediate length will be the sigma 2, and the smallest axis length will be sigma 3. That's how we construct the stress ellipsoid. Just as in case of a strain ellipsoid, where the maximum stretch is lambda 1 quadratic elongation, the intermediate will be lambda 2, and the smallest will be the lambda 3. That's how we know which are which. So going to the next question. The first stress invariant of the stress tensor is physically equivalent to the differential stress, the maximum shear stress, three times the mean stress, and the magnitude of the deviatoric stress tensor. So you may have to calculate based on the formula of the first stress invariant. So then I will give you some time. You may actually exercise these this question. So you have to find the relation between, it has to be represented, it has to be represented either in the terms of the differential stress or in the terms of the uh, hydrostatic stress. Yes,
Option
option C
C.
is the correct answer. So it is generally three times the mean stress or the hydrostatic stress, because the first invariant is I1 is equivalent to the summation of sigma xx, sigma yy, and sigma zz. Now we correspond the x-axis of the stress tensor, the coordinate axis x is equivalent to the largest, the largest length of the axis of a stress ellipsoid, and that is why we consider sigma xx as sigma 1. Similarly, the intermediate length axis, which is the y axis, and we coincide with these y axis corresponding to the intermediate length axis of the stress ellipsoid, so that is why it is sigma 2. And similarly, we considered the z axis as the smallest, and that's why it is sigma 3. So I1 is essentially the summation of sigma 1, sigma 2, and sigma 3. Now, since the mean or the hydrostatic stress is defined as the average of these three uh, principal stresses, right? It follows I1, the invariant, first invariant, is 3 times the mean hydrostatic stress. And that is why I1 is invariant. First stress invariant, it is invariant because under a change of reference of axis, it will not change because it is related to it is a function of the mean stress, and that is why it is an invariant. So the first invariant is invariant because it is the function of the mean stress. Would it have been some other other form of the differential stress, it would not have been an invariant, because differential stress and the Dimitrich stress both are directional property. Both of them have directional properties. But the first invariant is invariant because it does not have it does not have a uh, directional property. Right? Now, I may ask you a question: is that what is the difference between the differential stress and the Dimitrich stress? So, can you guess what is the probable difference between what is differential stress and what is a Dimitrich stress? So, any idea?
Differential stress is a scalar quantity and deviatoric stress is a tensor quantity.
Mm, Not essentially, because both of them are essentially tensors. Right? But the main difference is the differential stress is the difference between the largest and the smallest principal stress. So differential stress is essentially sigma 1 minus sigma 3, and David-Rick stress is the difference between the any of the principal stress and the mean stress. So if you construct a Mohr circle, right, then the diameter of the circle will be the differential stress, but the radius of the circle will be, diameter of the Mohr circle along the x-axis, obviously diameter of the Mohr circle along the x-axis will be the differential stress, but the radius will be the David-Rick stress, right? Did you get the point? So essentially, David-Rick stress, if you have the mean stress, you can calculate the or you can calculate the or if you know the David-Rick stress, you can calculate the differential stress, because differential stress is twice the David-Rick stress. Okay, so differential stress is basically the difference between sigma 1 and sigma 3, and the David-Rick stress is difference between mean stress and the and any other principal stresses. That's the David-Rick stress. Okay, so going to the next question. The eigenvectors of the stress tensor at a point define directions along which the shear stress is maximum, the traction vector is parallel to the plane normal, the normal stress is exactly zero, and conjugate shear fractures are oriented.
Option B.
Yes, the traction vector is parallel to the plane normal. That means, in other words, it is a twisted statement, because it is actually trying to say is that we only consider the normal tractions and not the shear tractions. So eigenvectors always represent the normal traction directions, because they then eventually will produce the orientations of the principal axis of stresses. And along principal axis of stresses, there will be no shear component, right? That is why option B is correct, because the traction vector is parallel to the normal, plane normal. Now, if we introduce the eigenvectors of a stress tensor, it will satisfy this equation. Right? You have already gone through this equation. So how these eigenvectors are calculated? So we get a normal, and we multiply that with so this one. So this is essentially what? This is essentially the tensor, right? And this is a vector, and you are getting a dot product, a vector dot product between these two quantities, and you equate this dot product to the direction of the plane normal with some scalar multiplier. So this is basically what? This is basically, this part n is a unit vector multiplied by a scalar factor. So this scalar factor is the magnitude, right? Magnitude of the what? Eigenvector, that is the eigenvalue. And it will eventually give us the length of the maximum or the minimum or the intermediate length of the axis of the stress ellipsoid, right? So together this quantity, it is the eigenvector. This is the eigenvalue. Lambda is the eigenvalue, and the lambda in entire thing, this is the eigenvector, and it comes from the dot product between these tensor and this vector. So that so it means that the traction vector produced on the plane with normal vector n is simply a scalar multiple of the n itself, and the traction is parallel to the normal with no shear component. These eigenvector directions are exactly the principal stress direction, and their eigenvectors are principal stress magnitude, right? So eigenvectors are, you know, eigenvectors are constants at any point. If it is maintaining a equilibrium, then it has to maintain the orientation fixed. If you impose some linear transformation into this system, all things will rotate except these directions, and that is why they are called the eigenvectors, because they are the actual references, because they are the actual axis of the stress ellipsoid, or stress ellipse if you consider a 2D situation, right? So if you impose a linear transformation, everything will rotate based on the linear transformation that you're imposing. That means you are changing the uh, you know um, aspect ratio of the stress ellipsoid. You're doing that, but what you're not doing is that you are not changing the mutual orientation of the axis of the stress ellipsoid. That means eigenvectors will always remain the same. They will not, they are not hampered by the linear transformations that you're imposing on the, imposing on that tensor and the stress ellipsoid. And it is only possible because you can only calculate the eigenvectors for a matrix which is orthogonal. That means it has to be a symmetry, and if there was no symmetry, and if the matrix were not if the matrix was not orthogonal, then you could not have calculated its eigenvector. It is not possible. And if there is no eigenvector, then you simply can't calculate the orientations of the stress axis of the stress ellipsoid. And that means that physically at that point the equilibrium condition will not be maintained, and that's why you're not getting any stress ellipsoid. Stress at a point, and in everything that is related to the stress at a point, it is connected through these geometries. Okay, so coming to the 10th question. Conjugate shear fractures generated by a given stress system are symmetrically arranged about sigma 3 bisecting the obtuse angle between the fractures, sigma 2 bisecting the acute angle between the fractures, sigma 1 bisecting the acute angle between the fractures, or sigma 2 bisecting the obtuse angle between the fractures. Okay, so the answer is actually sigma 1 bisecting the acute angle between the fractures. So if I just try to draw roughly, it's not actually perfect. So this is the acute angle. So sigma 1 will bisect. So this is how sigma 1 will work. And this is the obtuse angle. So sigma 3 will be bisecting the obtuse angle. And vertical to this point of intersection, like this, I mean in coming out of the plane like that, will be the intermediate stress sigma 2. So that is how conjugate shear fractures are being generated. So according to the Anderson's theory of faulting, conjugate shear fractures form symmetrically about the sigma 1 and sigma 3 axis. Right? Sigma 1 bisects the acute angle between the two conjugate planes, and sigma 3 bisects the obtuse angle. And sigma 2 is parallel to the line of intersection with of the two fracture planes. So the line of intersection goes right into the plane like this. If you have shear fractures like this, so the point of it, the line of intersection is basically lying vertically out of that plane. So sigma 2 is parallel to that direction. So that is how option C is the correct answer to this question. Okay, question number 11 is quite easy. For a linearly elastic isotropic material, the ratio of shear stress to the corresponding shear strain is defined as Young's modulus, bulk modulus, Poisson's modulus, and shear modulus.
Option D.
Yeah, of course, it is the shear modulus, which is also known as the rigidity modulus, is defined as the ratio of the shear strain to the shear stress to the shear strain. And this is distinct from Young's modulus because Young's modulus represents the axial stress divided by the axial strain. It is also different from the bulk modulus because bulk modulus is basically the hydrostatic stress divided by its volumetric strain. And Poisson's ratio is actually a dimensionless ratio between transverse to axial strain itself. Right. So that's how the shear modulus, or also known as the rigidity modulus, is being defined. Okay, so moving on to the next question then. So in coaxial or irrotational deformation, progressive deformation, the principal axis of incremental stress ellipsoid and those of the incremental strain ellipsoid are oriented at 45 degree to one another, unrelated in orientation, parallel to one another, always mutually perpendicular. Now go through the question carefully and think what is actually asking, and then answer. It is actually a very good question.
Option D.
Exactly, you're absolutely correct. Option D. Sorry, option C. No, no, actually, option uh, stress principal axis of stress ellipsoid and the incremental strain ellipsoid. No, they will be parallel to each other because as I mentioned that coaxial deformation is by definition deformation in which the principal strain axis do not rotate relative to the principal stress axis through deformation history, right? And the incremental stress and incremental strain ellipsoid share the same principal directions at every stage. And this is in contrast to non-coaxial rotation because, such as in simple shear, where the two sets of axes are generally not parallel. Now the thing is, the axis will remain same, but the aspect ratio of these two ellipse, or the strain ellipse and the stress ellipse, the axis may remain parallel, but their aspect ratios will be perpendicular to each other. And I know why you have guessed the answer is because the maximum stress is also the direction of minimum strain, right? So wherever you're compressing, so the compression direction, if the compression direction is sigma 1, and the corresponding stress ellipsoid will look like this if this is sigma 1, but then the sigma 1 axis will be parallel to the lambda 3 axis or S3 axis of the strain ellipsoid, because the maximum stress is the minimum strain and the minimum stress is the maximum strain, right? So the ellipses, aspect ratio of these ellipses will be perpendicular to each other. One will be like this, and with respect to that, the other will be perpendicular to it. But if you just simply follow the axis, they will coincide without any obliquity or any rotation in between them. If you consider a pure shear component, then of course something will rotate. But here, it will not rotate. Both of the axes for the stress ellipse and the strain ellipse, they will remain parallel. I mean, they will intersect orthogonally, but the aspect ratio of the ellipses will be perpendicular to each other, or the shape of the ellipses with respect to the maximum axis, right? The largest axis with respect to the largest axis, the shape of the ellipses will be, the aspect ratios will be perpendicular to each other, because the reason is stress and strain for coaxial progressive deformation, they are actually inversely proportional to each other. Maximum stress is equivalent to the minimum strain, and vice versa, right? So in a way you give the correct answer, but what what is actually happening is that the aspect ratios of the ellipses will be perpendicular, not the axis itself. They will remain parallel. I mean, they will both be actually crossing over orthogonally. There will be no angle between each other. Angle as in no obliquity. Okay. So this is a numerical question. So during an earthquake, the shear wave velocity and density of a rock are measured as 3200 meters per second and 2.8 grams per cc, respectively. Assuming a Poisson's ratio of zero point 0.3, what's the Young's modulus of the rock? Option A, 37.27. Option B, 57.34. Option C, 74.55. Option D, 96.28. So what you need So you have the Poisson's ratio, you have the velocity of the shear wave, that means the S wave velocity, and you have the density. So you can actually calculate the rigidity modulus if you know the S wave velocity and the density. And you can use that rigidity modulus to calculate the elastic modulus or the Young's modulus. So the shear modulus from S wave velocity is mu is equal to rho Vs square. So you know mu, sorry, you know the density and you know the velocity. So you can then calculate the rigidity modulus from this formula. So go ahead and do this numerical and let me know what is your answer you're getting about the rigidity modulus, and then we will further you know proceed with calculating the elastic modulus. So you have all these values. So you have the density, you have the velocity, and you can calculate the rigidity modulus. So let me know when you get the value, then we will proceed to the next level.
2.86 into 10 raised to 10.
Yes, it's correct. So of course you have to convert the you know mm, density into kilogram per meter cube. That gives you this value 2.86 into 10 to the power 10 Pascal. So it is 28.67 gigapascal GPa, right? And now you can use this formula to calculate the Young's modulus from Poisson's ratio and rigidity modulus. It is the E is equal to 2 mu by 1 plus nu. Right? You know the Poisson's ratio, and it is then you can calculate the Young's modulus.
Sir, in that formula, 1 plus mu should be in the numerator, no?
1 plus nu in the numerator. Why?
Because E is equal to 2g into 1 plus mu.
2g multiplied by 1 plus. Yeah, yeah, sorry. Yeah, you're correct. Yeah, if you eventually do this, then this Yes. Yep. So the correct option is option C, right? 74.55 GPA. Okay, thank you. So, moving on to the next question, then the stress state at a point is given by 60 megapascal of sigma xx, sigma zz is 20 megapascal, and shear stress component sigma xz or tau xz is 15 megapascal. Calculate the normal and shear stress components on a plane whose normal makes an angle of 30 degree with respect to the x-axis, right? So what we will do, we will consider the 2D stress formula, the simple Mohr circle formula. So we will calculate the normal stress like this, right? And so you have been given three things, right? So the normal thing, I mean, most of the numericals that you generally solve, you are only given with sigma 1 and sigma 3 and no shear stress components. So the thing is, there are three stress components given, not two. So that is why when we are applying the third component, stress component, we take the sine and cosine while calculating the normal and the shear stress components respectively, right? So this will give you the normal stress and this will give you the traction. So then you have to use these formula to calculate the normal stress and the shear stress component. So you note down this formula because normally in any numerical things, in any numerical exercises, what we will get is only the two components and the angle, right? And you will be asked to calculate, the normal and shear components just based on the principal axis of principal stress values. But along with these principal stress values, you're also getting a shear stress value. So how do you use that shear stress value? You use these shear stress components as well. So you have these normal stress formula. This is the simple Mohr circle formula. And additionally, there is a shear component to this one. Okay. For normal stress, you will simply take the sine component of the 2 theta angle, and for the shear traction, you will simply calculate the you will take the cosine of the 2 theta component, and you will just simply add that value. So the mean value is 40 MPa, and the half difference is or the half differential stress is 20 MPa. 2 theta is 60, cos 60 is zero point 0.5, sin 68.86, and if you simply plug in the values, so you will get, sigma n will be equal to 63 megapascal, and if you just plug in the value of shear component, you will get 24.82 megapascal. So the resolved normal stress will be 63 megapascal, and resolved shear stress component, sorry, this will be 24.82, not 9.8. So this will be 24.82 megapascal. Right? So I think you should take a screenshot of these formula if you are, so it will help you to actually use this formula. So it's an extended formula of what we generally uh, calculate for stress on a surface, right? So it's an extension with uh, addition to a shear stress component. Okay, so let us move on to the next question. A rock mass at a depth of 1.2 kilometers has an average density of 2750 kilogram per meter cube. The maximum horizontal stress is 45 megapascal and the minimum horizontal stress is 28 megapascal. Calculate the vertical stress from the overburden, determine the deviatoric stress state, and identify the likely faulting regime. So we have three targets. So we have to calculate first the vertical stress and the deviatoric stress, and based on the relation between the vertical stress and the deviatoric stress, which kind of Anderson's fault theory it would generally go with, right? So the vertical stress or the overburden will be simply the overburden pressure, and you can simply calculate that using the vertical stress is equivalent to rho gh, right? So 2750 times 9.8 times 1200 in meters, and that would give you 32.34 megapascal. So this is the this is the vertical stress. Now if we calculate the mean stress, it will be 45 plus 28 plus 32.34, which is around roughly 35.11, right? Now deviatoric stress will be, you simply subtract the mean stress from the given stresses. So the horizontal maximum stress will be 45 minus 35, which is a positive note, positive quantity 9.89. And if you just simply get rid of the minimum value, so 28 minus 35.11, it is minus 7.11 megapascal. So what this stress means, so anything having a minus sign would mean it is tension, right? No compression, it is going to tension. And the vertical deviatoric stress will be also in tension. So the maximum deviatoric stress coming from the side horizontally, it is positive, but the other two directions they are negative, right? So ranking the total stress, obviously sigma 1 will be 45 and sigma 2 will be the vertical situation and sigma 3 will be the horizontal situation, right? And since the vertical stress is the intermediate principal axis, with both sigma 1 and sigma 3 are horizontal, the stress state corresponds to a strike slip faulting in the Anderson's classification, right? So that is why in along one direction there is compression, and along one direct and the other two directions you are having tension. So that is why in relation with respect to the compression and to two mutually perpendicular tension regime, it will tend to produce a strike slip faulting. Okay, so moving to the next question. So the principal stresses at a point are sigma 1 18 megapascal, sigma 2 is 12 megapascal, and sigma 3 is 7 megapascal. Calculate the magnitude of the first and the second stress invariants. So of course the first invariant will be summation of the all three principal stresses, and the second invariant is what? It is the product of the mutually perpendicular principal stresses. I mean, it is a summation of the products of the mutually perpendicular principal stresses, right? So I2 will be essentially sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 1 into sigma 3, right? So that is how you calculate the second stress invariants. It is simply the summation of the products between the immediately mutually perpendicular principal stresses. Sigma 1 times sigma 2, sigma 2, sigma 3, and sigma 3, sigma 1. And you get a value of 426 megapascals, square of megapascal. Now the thing is, why this second invariant is an invariant, not a scalar. I mean, why is it a scalar and why is it not a vector or a tensor? What do you think is the reason? Do you know the reason? The reason is very simple, because it's a square. It's a whole square value, right? And that cancel out any directional component, because we are simply producing the magnitude. You're taking the whole square, so that is basically the magnitude and not the the direction component is missing out. It's essentially it's like the dot products between the mutually perpendicular things. So if you take dot products, like in cases, it will obviously produce, and it will obviously cancel out the the direction components. So that's why it's just the square of the magnitude. It's just a value. It's a scalar, and that is why it is invariant. It is invariant because it does not have any directional property. Okay, so another question. A rock mass at 800 meters depth has an average density of 2800 kg per meter cube. The maximum horizontal stress is 32 megapascal and the minimum horizontal stress is 20 megapascal. If fluid injection raised the pore pressure to 12 megapascal, calculate the effective vertical and horizontal stresses experienced by the rock mass. Right, so you need to calculate the effective stress. But for doing that, what we need, first we need the overburden pressure, and it is simply rho gh, right? So you plug in the values of the density, acceleration due to gravity, and the depth, and you get a value of nearly 22 megapascals, right? Now, effective stress is essentially the difference between the principal stress and the pore pressure. Right? So, pore pressure is essentially equivalent to the mean stress. So, you are essentially calculating a Davitric stress, but in a different sense. So, that's how we eliminate or subtract the pore pressure from the principal stresses, and that's how we get the values. So one is, of course, 32 megapascal is the maximum horizontal stress, and it's 32 minus 12. The minimum horizontal stress is 20 minus 12, and the vertical effective vertical stress will be 21.95 minus 12, 9.95. So that is how we get the effective stress. We simply subtract the you know pore pressure. Okay, so the principal stresses in a rock mass are 50 megapascal, 30 megapascal, and 10 megapascal. And calculate the maximum shear stress and state the orientation of the plane on which it acts relative to sigma 1. So of course the maximum shear stress will be where theta is 45 degrees and 2 theta is 90 degrees, and that's how sine 90 degrees is 1. So we eliminate that part, it becomes 1. And so simply it is sigma 1 minus sigma 3 divided by 2, which is 20 megapascal. And this maximum shear stress acts on a plane oriented at 45 degrees to both sigma 1 and sigma 3, the plane bisecting the angle between the sigma 1 and sigma 3 directions will be the maximum shear stress localization plane, right? Okay, so the stress tensor at a point referred to the xz plane has components of sigma xx 44, sigma zz 18, and tau xz 13. Determine the principal stresses or the eigenvalues and the orientation of the principal axis relative to the x-axis. So we need the eigenvalues and the orientation with respect to the x-axis. That's it. What you've been given two principal stresses and one shear stress component. So the first thing you do, you calculate the mean stress, which is 31 megapascal. And then you calculate the radius of the, the radius of the effective um, Mohs circle. And that you calculate using the maximum shear stress calculated from the given principal stresses and the shear stress given in the problem itself. So you take square root of the addition of these two components. So first you calculate the maximum shear stress component given from the principal stresses, and you add the square. So it is like root over of a square plus b square. It's the same formula that you apply in Pythagoras's formula, right? You calculate the resultant value or the magnitude. And the same principle, using these two stress components, you calculate the maximum shear stress component, and you use that to calculate what we call as the mean length or the radius, or which is actually the magnitude, which is 18.38 megapascal. And this will be your radius. Means if you just plot a Mohr circle, the center will be at it at from the center to at any point on the circle will be 18.38. So you consider that you're constructing a Mohr circle. So you're basically finding the center position, which is the mean stress, and then eventually you're calculating the radius from the, because in the Mohr circle the y-axis will be the shear stress and the x-axis will be the normal stress, right? So you calculate the maximum shear stress component and the given component to actually calculate the effective radius of the circle. And then what you do, you calculate the principal stresses based on the circle. So one will be 31 based on the mean stress plus 18.38, and the other one will be 31 minus 18.38. So that's how we calculate sigma 1 and the other part, whether it is sigma 2 or sigma 3, anything, right? Because we are constructing in a two-dimensional plane. It is, as mentioned, the xz plane. That means it is a 2D strain problem. Now the orientation is of course from the formula half tan inverse twice the shear stress given divided by sigma 1 minus sigma 2. Right? This is the formula we generally use for measuring the angle between some orientation with respect to the uh, plane of plane of stress, right? And the value is 22.5 degrees. So the maximum principal stress direction is rotated 22.5 degrees from the x-axis. So eventually if you plot that in a Mohr circle, so what we are actually calculating here numerically can also be done from the Mohr circle. Oops, sorry. So so this is the center. You can write sigma m. This will be sigma 1 and this will be sigma 3, right? And this is some shear stress value given. So you calculate what will be the normal stress at for these shear stress value given, and you also calculate the radius from the maximum shear stress. So this is the maximum shear stress that you can get. So you calculate the radius and then construct the Mohr circle, and you then plot in the Mohr circle the corresponding shear stress value and drop a projection, and you will eventually get the value which corresponds to that particular shear stress value. and then you measure this angle and you simply divide it by 2, right? So essentially what you have, you will have a right angle triangle like this in the Mohr circle, and you simply take the inverse of the tan, and that's how measured the angle between the mm, sigma 1 relative to the x-axis. Okay, so the last question: the stress tensor at a point is given by sigma xx is equal to 50 megapascal, sigma yy 30 megapascal, and sigma zz as 20 megapascal, and a shear stress component on the xy plane as 10 megapascal, and consider all other shear stress components as 0. Calculate the traction vector acting on a plane. Those unit normal is n as 0. 0.6, 0. 0.8, and 0. So you calculate the traction as the product between the stress and the unit vector value, right? So the traction for, in this case, x direction will be sigma xx times nx plus tau xy into ny, right? So that's how you resolve the components of the stress tensor, right? You simply multiply it with the, or you take the dot product of the along the, I mean between the dot product between the, the unit vector and the magnitude of the stress given. So it will be 50 point times 0.6, because 0.6 is the normal unit normal value along x direction, and the unit normal value along y is given 0.8, and for z it is 0, right? Similarly, you calculate tz, you get this value, and for tz is equal to 0, since nz is 0 itself, and there is no xz or yz shear coupling, because only the xy shear stress is given and all other shear stress components are considered as 0. So the traction vector T comprises of 38, 30, and 0 megapascal unit. So for one single point, 3 different orientations. So this is a vector, right? So there are 2 different orientations. And if you simply calculate the magnitude by the taking the resultant between these two values, and which is around 48.44 megapascal. So that is how you apply the relation between the stress tensor and the unit vector to calculate the uh, traction component. So with this, we discussed around 20 problems on the concept of stress, and I wish you a happy Independence Day, and thanking for joining these on this weekend. So with that note, I am ending today's discussion session. So we will in the next week, we have an interesting topic on the rheology itself. It's a very interesting topic, and we will also exercise some conceptual numerical problems related to rheology. So until then, thank you and goodbye.
Happy Independence Day, sir. Thank you.
Same to you. Thank you.